Hello, once again. I'm Fedor, and this is a joint work with Itai Arieli and Rann Smorodinsky. Think of a particular consumer's dilemma. For example, choosing between Android and iPhone. Usually we have our own gut feeling of what is the best alternative. So we get such a noisy private signal about the ground truth. And we also observe choices made by our friends who faced similar dilemmas in the past. And it is known that even the society of perfectly rational Bayesian agents may fail to aggregate such gut feelings. The reason is the following. If first few agents happen to get wrong signals, they take wrong actions, then those who come next, they observe these wrong actions. They think that so many predecessors cannot be wrong, and they ignore their own private signals and repeat this wrong action. And so the avalanche of wrong actions propagates through the society. We get the so-called global information cascade when the actions of the first few agents determine the actions of the rest of the society. Whether or not such cascades originate depends on the underlying friendship network. And the literature offers some topological conditions on this network that guarantee that the society, that the network aggregates information very well. But there is one subtlety here. These conditions and the analysis itself are tailored for a particular order of agents' choices. So in a sense, this corresponds to the situation when the timing of my choice determines the structure of my social connections. This can be a reasonable assumption if we think of big decisions, some life-changing decisions like choosing a career, but it clearly does not fit the Android-iPhone dilemma. And our paper is motivated exactly by small casual decisions, like buying cheap stuff. And in this case, it's reasonable to assume that the network, the social network, the structure of our social connection, they pre-exist and they have nothing to do with the timing of decisions. And we decouple the two, the network and the order, by assuming that the network is given, the network is fixed, and the order is random. A similar model was also considered by Bahar and others who analyzed a particular family of networks given by bipartite graphs, and they showed that within this family there are networks that aggregate information very well. But our goal and our contribution are different. So we aim to find some specific features of the learning process that distinguish the model with a random order from its fixed order cousin. In particular, we will see that agents' decisions become almost independent if agents are far enough, which means that long paths of information transmission disappear. This rules out global information cascades and also implies that the quality of agent's decision is determined by the neighborhood of this agent in the network and not the global topology of the social network. Okay, so let's look at it more formally. Here is the model. The network, the social network, is just an undirected graph. Vertices are the agents and edges correspond to the friendship relation. So it's mutual since the network is undirected. There is an unobservable state variable theta, which is binary, and for simplicity, it takes the two values equally likely. Agents are ordered randomly, and they take actions sequentially according to this order. Actions are also binary, and the agent's goal is to take an action that matches the state. So if the agent succeeds, then she gets the utility of 1, otherwise she gets the utility of 0. And the agent action can depend on the information that this agent has. And this information consists of a binary signal, a binary private signal about the state. So the signal matches theta with some probability p greater than 1/2. So the signal is informative. And of course, the signals are IID conditional on the state among agents. Also, the agent observes the set of friends, his immediate neighbors in the network who acted earlier, and the actions they took. In this description, the fact that we focused on binary state, binary actions, and binary signals is just to fix the ideas. So it's not so critical. So given this description, we get a finite Bayesian game. So it has an equilibrium, and we are interested in this equilibrium behavior. So I stress that agents do not rely on any heuristic to come up with their actions. So their actions are dictated by their equilibrium strategies. So the equilibrium strategies tells them how they should weigh the information that comes from their friends and their private signals, and how this information should be combined in their action. The difficulty with this approach is that this equilibrium cannot be constructed explicitly, even for toy examples. So all our proofs are kind of indirect. We cannot write down the formula for the equilibrium and analyze them. So it's an obstacle, of course. So let's see what can we say about the equilibrium despite this obstacle. So the first phenomenon that we observe is that agents have a bounded radius of influence. Namely, the agent's action is unlikely to affect those agents who are far enough. Formally, we prove the following theorem. If the distance between the agents V and U is large enough, namely it is higher than 8 times the maximal degree, then the probability that their actions are independent is exponentially close to 1 as a function of the distance between the two agents. To explain the intuition behind this result, let's look at a line graph where our agents V and U are the endpoints. And let's discuss how can it happen that the action of the agent V affects the action of U. So our goal is to see that it happens with very low probability. First of all, the only agent that can possibly see the action taken by V is the agent V1. So this action should be observed by V1, which means that V1 acts after V. Then the action of V1 similarly should be observed by V2, which means that V2 acts after V1, and so on. We see that the only situation, the only ordering of agents at which the action of V can affect U is when V comes first, then V1, then V2, and so on. So it happens for one ordering over possible D+1 factorial, where D is the distance between V and U. And the corresponding probability is very low. It's 1 over D+1 factorial, and it decreases fast in D. Of course, to rule out the dependence between actions of V and U, we should also eliminate the possibility that there is another agent, say W, that affects both of them, and we should also extend the argument to general graphs. But I think this example illustrates the intuition, why actions become independent when the distance is large. Now let's discuss some implications of this phenomenon. First, on the network level. So consider a network of large diameter. So the diameter is much bigger than the maximal degree. Then we can find many pairs of agents such that they are far enough to make their actions almost independent. It means that these agents cannot be part of the same information cascade. And we see that in such networks, global information cascades become unlikely. It means that the networks that exhibit cascade behavior, they split into many local cascades. And if we look at the paper of Bikhchandani and others, they interpret a Phation as an information cascade. So our corollary can be seen as a reflection of the fact that different Phatians can coexist in the society. Now let's look at a possible outside observer, an agent who sees all the actions taken by everybody else in the society. For example, the learning happens on a social media platform, and then this platform can be seen as this outside observer. Each local cascade is more likely to be on the correct action than on the wrong one. And so this outside observer observes many independent informative signals about the underlying state theater. So each cascade, each local cascade can be seen as such a signal. And so this outside observer can determine the state with high probability. Now let's discuss the implication on the agents level, on the individuals level. The bounded radius of influence suggests that the quality of agent's decision is determined by the local structure of the network around the agent. And we confirm this intuition. So let's consider the following number, the number of social circles bridged by an agent V. So the number of communities bridged by this agent. Formally, it's defined in the following way. So we look at the neighborhood of our agent of radius 8 times the maximal degree, the familiar number. We eliminate the agent from this neighborhood, and possibly the remaining neighborhood splits interconnected components. These connected components correspond to these social circles, to these communities that without agent V become disjoint, and the agent V bridges these communities. And so the number SV is just the number of such connected components. And we prove that if the number of social circles bridged by V is large, then the agent V is likely to take the correct action no matter how well other agents are doing. So even in those networks that are prone to information cascades, the agent bridging many social circles takes the correct action with probability that is close to 1. The proof is quite heavy and technical, but the overall idea is simple. So our agent V uses her friends from these connected components as sources of information. It can be shown that these sources are informative, and thanks to the bounded radius of influence, these sources are almost independent. And so our agent aggregates many almost independent informative sources, and so takes a well-informed decision. One can ask if there are networks where the number SV is large for all agents. And the answer is positive. And for example, it's given by Ramanujan expanders or any other network that has large degrees and no short cycles. We immediately get the following corollary. So fix any delta greater than 0, then there is a network such that the expected fraction of correct actions is at least 1 minus delta. And actually, existence of such networks was known from the paper of Bahar and others. What is surprising is that this network also has an extreme robustness property. Namely, we can eliminate almost all the population adversarially, and the remaining network will still aggregate the information very well. Still a 1 minus delta fraction of the population, of the remaining population, will take the correct action. Okay, it's time to conclude. So the main takeaway is that social learning with random order of agents is a convenient model if we are interested in causal decisions. In this model, long paths of information transmission disappear and global cascades become unlikely. The quality of agent's decision is determined by the local structure of the network around the agent, not the global one. And to guarantee the high quality decision for an agent, it's sufficient to bridge many social circles. In particular, if you want to make well-informed decisions, you should ensure that your colleagues do not know your family members and do not know your former classmates. That's it. Thank you.